Yeah, I will talk about a collaboration with Christian Giardina from Modena and Jorge Kurchan from École Normale that we started actually 2 years ago. And this is my first slide. I would like to thank the organizers because this work, this talk would not exist otherwise. It was in 2 years ago where I met Christian. He was speaking on Friday about probabilities, and I was speaking on Monday about Q operators, and then we started to discuss and found some common topics. And also, I had to learn about these integrable stochastic processes, and there are some nice reviews about this. So I also like to thank these authors. So, okay, this is the content of this talk. I will introduce non-compact spin chains and discuss how they can be interpreted as stochastic particle processes. In particular, I talk about the XXX chain, the XXZ chain, and the XXX with open boundaries. And then in the second part, I will talk about hidden equilibrium in the SEP, or also in this XXX non-compact chain, which allows you basically to compute steady state and things like this. Good. So we saw this picture already, this pipe for the ASEP or for the SEP. These are two integrable stochastic particle processes that are very famous and well studied. This basically is a nearest neighbor hopping model, and you only can have one particle per side. So the jumps are forbidden if there's already a particle on the side. And then most of this model comes with closed or open boundaries as you like. And here this is with open ones. So you insert particles with a rate delta, and you extract them with a rate beta. The hopping rates in the bulk, L and R, they are equal to 1 for the SEP and different for the ASEP. Good. So this is the Markov matrix for this process that generates it. So we have here these densities. It looks very much like the Hamiltonian of the spin chain. So this W, this contains the rates. And here these BL and BR, these are the boundary terms. And what is important to be a stochastic process is that the sum over these over the columns must be 0. And the off-diagonal entries must be of opposite sign than the ones on the diagonal. Good. This can be mapped to the XXZ spin chain or the XXX spin chain, and basically the Markov generator is just related to the Hamiltonian by some similarity transformation. Good, and then as we already heard in the last talk, you can apply Bethe-Ansatz methods to study this problem. And also I'd like to mention that there are multi-species generalizations where you look at higher rank spin chains. Okay, so we already heard also in the last talk that sometimes this maybe is an advantage, and sometimes it's not, that you cannot overtake other particles, and here probably is not an advantage that you cannot overtake, because this RSEP and SEP, they produce traffic jams, and we all don't like traffic jams, I guess. So this is a picture from a péage, I think in France, somewhere after the holidays. And the solution to this would be to put particles on top of each other, like here in this futuristic movie where the cars can go on top of each other. And people have thought about this, I think. But the naive observation is that higher spin I mean, okay, so this would be a higher spin model with more excitations than spin up and spin down. But the higher spin integrable models, their Hamiltonians naively are not stochastic. And the other way around is if you introduce such a model and you choose some stochastic rates, then they are very likely, or they are not integrable. And the way out is to look at these non-compact spin chains, where you can basically put infinitely many particles on top of each other. And it turns out that these are stochastic. So this is a slide about these non-compact spin chains. They are studied in high energy QCD and goes back to LAPTh and Fadeev and Khochemsky, I think, most of it. And then they also appeared in N=4 super young mills, and were also studied for pure integrability reasons by these people. So the quantum space of these spin chains is described here. You have a tensor product of n sides, and each side can be occupied by infinitely many particles, so mi goes from 0 to infinity. And then the generators of SL2, they act locally onto these cats in the standard way. So S plus raises the particle number, S minus lowers it, and S0 is diagonal. And you see if S is not a negative half integer, then you can continue to create as much as you want. Okay, so the Hamiltonian of these spin chains has been known, but was written in a rather funny way by Fadeev and his collaborators or students. And it's this nice d gamma function, psi, that and the argument is this curly S, which is an operator. I mean, this is the density, and S is an operator that acts on two sides, and it's related to the two-side Casimir in this way here. And I say a bit more about this operator S now. So if we have two sides of spin S, then we take the tensor product, and the irreducible representations that come out are infinitely many of representation label, or with representation label, to S plus J. And this S acts diagonally on these two sides, and the eigenvalue is just given by 2S plus J. So we can immediately compute the eigenvalue of the Hamiltonian on these irreducible representations, and it's basically these harmonic numbers which come from the psi function. But from here you cannot tell if the process is stochastic or not, and we would like to have a matrix that acts onto the two sides. So what one does is to use the Clebsch-Gordon decomposition to go back on the left-hand side of this equation here. And this has been done by Bizard in the context of N=4 super young mills. And this is what he got. So H acts as follows. There's a diagonal term where you have the harmonic numbers. And on the off-diagonal, you have a rate, 1/k. And you move k particles to the right. And you have a term that moves k particles to the left, but also with the rate 1/k. Okay. So in this, Hamiltonian actually is stochastic. Yeah, so the sum of the columns, the sum over 1/k is the harmonic numbers. And, everything has the right signs. So here I wrote it in a block form for two particles. And you can convince yourself that this works nicely. Okay. Now we can define a Hamiltonian, or the Markov generator, of a process with infinitely many or possibly an unbounded number of particles at each side, and k particles hop to the left and to the right with the rate 1 over k. So this is symmetric hopping. There's a generalization of that. You can take arbitrary s, and these coefficients were computed by these two people here, I think. And you get some gamma functions, or if you like, factorials, that depend on m, which is the number of particles at the given site, so of the departing site. And this is usually called, I think, a zero-range process. Yeah. It has a highest, I mean, it's always the highest rate representation, but I think you could relax it, and I'm not sure about this. So I think maybe you only have to be careful if you have negative half integers. Okay, so up to now I've been just reinterpreting results that have already existed, but people didn't recognize this connection. And what I would like to do now is to go to more complicated models that have like a drift or something like that, that you can that the particles prefer one direction to travel. And one way is to Q-deform, get something like the XXZ analog of this chain, or like an asymmetric process. And the other way is to introduce boundaries to the symmetric process. Okay, so the harmonic action is not, or was not known for the trigonometric case, but this Faddeev formula has been written down by Bitsko, and is basically the same, but now you have the Q-deformed gamma function psi Q. And S, okay, S is also again related to the two-side Casimir, which is defined like that. And you can undiagonalize this H as well, and what you find is quite interesting, or was at least was very interesting to us, that the resulting Hamiltonian can be related to the so-called Q-Hahn process by a similarity transformation, pretty much like in the A set. And this Q-Hahn process is a rather popular model, I would say, for mathematicians mostly maybe. And it was defined by Sasamoto and Vadati, Pofolotsky and Barak and Corwin. And it also belongs to this KPZ universality class, if I understand correctly. And also there are some nice relations to random matrices. So this summarizes a bit what I just said. Here on the left, these are the stochastic processes that were known. So the Q-Hahn process and this MADM, this was defined by Sasamoto and Vadati, which is a limit of this Q-Hahn process. And what I just said was that these can be mapped to the non-compact XXZ chain with spin S. If you take S equal to 1/2, then you recover this MADM. And if you send Q to 1, you go to these non-compact XXX spin chains that I introduced in the beginning. So these green ones here, they are stochastic. And okay, the spin chains, they are not, but after the similarity transformation, they are. Okay. So now I'd like to add these boundaries to the symmetric process. So I'm looking for some Hamiltonian or Markov generator of this form, where this H these hopping rates 1 over k that I introduced. And well, you have to come up with some nice boundary rules. Yeah. And this was Christian who actually then guessed a nice boundary term. So particles can leave the chain with the rate 1 over k, and they are inserted with the rate beta to the k over k, where beta is some parameter. And the big question then was if this Hamiltonian here is integrable or not. And what I would do if or what I did when I got this question was I looked for the corresponding K matrix.
Sorry, which says that this was guessed? Which was the property you were asking for the boundary terms?
Sorry, again?
Which condition you asked on the boundary terms? I mean, just that was so wide was against.
Yeah, I'm not so sure we should. This is a question that Christian could probably answer, but I think it had to do with reversibility. Okay, so the K matrix that is needed for these non-compact spin chains should satisfy a boundary Young-Baxter equation like this here. So we have a fundamental representation, and S stands for this arbitrary spin. And in this space, I take arbitrary representations, basically just algebraic generators. I don't even say anything about the representations. And the K matrix here, this one we know, this is the most general one. Okay, for now, let's solve the most general problem. So it has 4 parameters, Q1, Q2, Q3, Q4. And then you would like to solve this equation for this curly K, which is, this vertex here. And to my knowledge, this has not been done. And but it's once you make the right ansatz, it's rather simple. So you redefine these parameters, and this is a useful parametrization, where now these alpha, beta, gammas, deltas, they have nothing to do with the boundary rates. And you make this ansatz here. So the off-diagonal parts are on the outside, and there you have an inner part, K0, that is diagonal and only depends on the Cartan element. And if you plug this into the Young-Baxter equation, you end up with a difference equation in this variable S0. And this you can solve, and you find these gamma functions. So this is quite a nice formula, I think, for spin chain people as well. And if you now plug in any representation for these S's, you should recover the K matrices. To derive now these stochastic boundary conditions, one has to set this fraction of delta over gamma equal to S minus 1/2, and alpha is equal to 1 over 1 minus beta. And then one can just compute the Hamiltonian using Sklernin's prescription, and one arrives at this expression for the boundary terms, which is even more general now because we didn't set S equal to 1/2, and we also get, that's why we get here these gamma functions additionally, which disappear for S equal to 1/2. So to conclude then, this process is indeed integrable. So further interesting properties of the model is that there is a dual stochastic process of finite particles, which has an absorbing, it's an absorption process, and the absorption probabilities, they can be used to recover this information about the steady state. And the long wavelength limit, this is maybe a nice observation, that this in this ADS-CFT community, this corresponds to a rotating string. And here it is the hydrodynamic limit of the particle process. Good. This K matrix, I wanted to say something about that. there were some attempts to generalize to XXZ by Tsuboy and Mangazeev and Lu, but they only came up, I think, with triangular solutions so far. But still, you don't necessarily have to solve this boundary and Baxter equation to find the integrable stochastic boundaries for the Markov generator. And so you could also extend this to the Q-Han process. Okay, so what we ask next, and I have a few minutes. Okay, perfect. What we asked next was if we can find the steady state of this non-compact XXX with boundaries. And somehow it's not so clear how to use this DHP-Ansatz, the matrix product Ansatz, because you have, if I understand correctly, would have infinitely many different Ds and Es to commute. So we try to come up with something different, and this I would like to now present for the SEP, but it also works for this non-compact model. And in fact, maybe the results were even better than we expected. So I come back to this exclusion model now, with the matrix hoppings in the bulk, and the standard rates at the boundary. And what we found was sort of a theorem that once for the spin chain people, there exists a similarity transformation W that maps the XXX spin chain with lower or upper triangular boundaries to the spin chain with diagonal boundaries. And this statement, if you translate it to the particle process people, then this is roughly saying that there exists a transformation W prime, which maps the Markov generator H of the open SEP with arbitrary rates at the boundaries to its equilibrium where you identify these rates. Good. And this is kind of has been proven by construction of this W. So there's a similarity transformation applied on the Markov generator of the equilibrium that maps to the general Markov generator. This is what I just said in the formula. And this W up to some local terms that I didn't write is given here. So it's a rather complicated thing, but it's a finite sum, k from 0 to n. These are the gamma functions. These big gammas, they are related to these boundary parameters. And, well, a lot is hidden in this Q minus, which is a non-local charge of the transfer matrix, which you can extract at order x to the 2n. And this is this one here. So as you see, it is very non-local, which you would probably expect. Okay. So this W can then be used to map the equilibrium, or the steady state of the equilibrium to the steady state of the non-equilibrium, like here. And something similar was observed by Tailleur, Kurchan, Lecomte, and Bertini, if I understand correctly, in this macroscopic description of the model. And you arrive at some nice formulas here that I want to show as the last thing. So the probabilities in the steady state, you can write a closed form. Here this last part is very similar to a beta, to the coordinate beta ansatz wave function. Here this looks somehow like an S matrix, but it's not so bad. This And for the k-point correlation functions, the moments, this is even easier, the expression now. These rows, did I define them before? Yeah. They are related to the alpha, gamma, beta, delta. Okay. So we didn't use any DEH P algebra here. And furthermore, what is very was puzzling at the beginning somehow, that we also didn't solve any beta equations. So this was just an algebraic. I mean, yeah, somehow we used these generators of the transfer matrix. Okay, and this works the same in the non-compact model. Good. So, conclusion, there are very interesting connections between high energy physics, quantum groups, condensed matter I wrote here, and probability theory. And we saw that these Q-Hahn type models, they are described by these non-compact spin chains. And for me at least, this answered quite some questions that I had about these models. Then I probably convinced you that the quantum inverse scattering method can be useful to study integrable stochastic processes. So we found the integrable boundaries, and also we found a way to obtain the steady state. And finally, what I would like to stress now again, that we map the open set to its equilibrium. Outlook and open problems. So for the non-compact case, there are these processes, TATS-RIPS, which is basically the Q-Hahn process, but only going in one direction. So like a totally asymmetric, like the TAR set. And what I'm interested in is where these generators, how they arise from the quantum inverse scattering method. And one place where I expect them to appear is from Baxter Q operators, that these charges, that the Hamiltonian that you can extract from the Baxter Q operator is exactly the one of these total asymmetric processes. Then there are these generalizations to SUQn(1) in this framework of the stochastic R matrix by this Japanese group, which describe the multi-species generalizations of the models that I talked about. Then one might ask if there are any implications for ADS-CFT. We tried a bit to think about in this direction, that at one loop you have the Hamiltonian is known, and maybe one can reinterpret this as a stochastic process. Then for compact chains, what I said in the end, it's not so clear how this generalizes to the ASAP. This seems much more complicated, but maybe with this off-diagonal beta ansatz and separation of variables that we heard a lot about, one can actually do something. And finally, I'd like to mention this quantum set that we also will hear more about later. So maybe one can generalize also there. So, of the things. Thanks.
Any more questions? For ASAP, for example, we know that special measure in periodic chain is trivial. What happens for non-compact?
No. I think it's the same. It's probably also.
So you didn't look at the.
Not at all, no. No, not at all, no.
You said when you have this S-set model with a bound number of particles in each side, the probability to jump, like to make k particle jump, is 1 over k. How come? Like, why this probability is chosen?
Yeah, that's a good. Okay. So this was for the symmetric process. Actually, the 1 over k is for the symmetric one. So This is not that. So the rates, well, they are even more the ones for the asymmetric, for the Q Han. Okay. How come? Yeah, it's a good question.
Okay, it's just a guess, and then we show it's integrable. Or?
Well, the way it came up was okay. So the spin chain has been studied, and you can basically just look at it and you observe it. So, but yeah, it's a guess, and in the sense that also when Christian talked 2 years ago, he was suggesting a model where you take the two-side Casimir, but the generators you take from these non-compact spin chains. But then if you know more about integrability, then you know that this is not the right Hamiltonian that is integrable. So then you ask the question, what is the right Hamiltonian? And then you see, yeah.
One question. How did you construct this non-local similarity transformation to make the modality?
Yes. So this is actually this kind of perturbation theory in the end. I think so that you really you take the equilibrium process and you view it, or you take the process and you view it as a perturbation around the equilibrium, and then you do perturbation theory, and it turns out that if you, in the integrable case where you have these these charges, you can just use one of these charges to really then sum up this perturbation. I hope this kind of.
Okay.